Start, sir.
Welcome back to our YouTube channel TREIS. So previous class we have discussed about the chemical kinetic chapter. So this is the second class in that chemical kinetics chapter. So in this chapter in this lesson we will discuss about the molecularity of the reaction. In the previous class we have discussed what is the need, what is the requirement to study the chemical kinetics, how rate will be depends. Okay, what is the rate, what is we have discussed in the previous class. So in this class we will discuss about the some more about the rate of a reaction. Okay, so rate will be depends upon the especially three factors. One is concentration, second one is temperature, and third one is catalyst. These three effect will be depends these three will be depends on the rate of a reaction. So first one, concentration effects, those comes under all these, whatever rate, molecularity, first order, zero order reactions, all those comes under the what is that one, concentration effect. So in this we will discuss about the molecularity of a reaction. What is molecularity? So the number of reacting species that are involved in the rate determining step, here RDS, rate determining step, those are called as molecularity of the reaction. What is rate determining step? In a chemical reaction, if any chemical reaction it happens in a single step, that is called as elementary reaction. If more steps are there, that is called as complex reactions. Okay, yeah. So in a complex reactions, okay, so whatever the rate determining step is there. What is rate determining step? In a chemical reaction, more than one step is present, then slowest step, whatever the slowest step is called as rate determining step. In that slowest step, how many molecules are involved? That is equal to molecularity. For example, we are taking based on the noun number of the molecules involved in the rate determining step, we can categorize it especially into three types: unimolecular, bimolecular, trimolecular. Okay, what is unimolecular reaction? If in rate determining step only one species is involved, that is called as unimolecular reaction. Ammonium nitrate NH4NO2 gives N2 plus 2H2O. In this, how many number of reacting species are involving? Only one reacting species is involving, that is called as unimolecular reaction. If two reacting species are involved, 2HI, hydriodic acid, hydrogen iodide, here two species are present. Two, coefficient 2 indicates the two species are present. That's why here bimolecular reaction. Here two NO species and one oxygen species. Three species are present. That's why this is termolecular reaction or trimolecular reaction. Yeah. Next, we will discuss about the integrated rate equation. This is important. So, how to derive the rate equation, integrated rate equation for the zero order reaction and first order reaction. This is important. So, yeah, we have to derive the integrated rate equations. For that, what is integrated rate equation actually? So we know the instantaneous rate equation. Instantaneous means, so for a particular time we are taking different concentration. First class we have discussed, we are taking different concentration one axis, in another axis we are taken time, different time inverse. At a point, at particular point we can take, so some rate, that is called as instantaneous rate. But in common we have we can derive the zero order reaction rate and first order reaction rate and also second order reaction rate. How can we derive? We will see here different types of reaction rate. So what is first order reaction? So we have discussed what is order. Sum of concentration, sum of powers of the concentration terms in the rate equation, that is called as, what is that one, rate. So here rate equal to k into a power 1. Here 1 is there, that's why it is first order reaction. Rate equal to k a square. So sum of powers of concentration terms equal to here 2. That's why this is comes under the second order reaction. What is zero order? This one. Rate equal to k into a power 0. That means independent of the concentration of the reactants in the zero order reaction. Now we have to derive the one by one zero order as well as first order reaction. So first we will see the integrated rate equation for the zero order reaction. So here R is a reactant, it is converting into the product. R gives to P. So rate equal to minus dr by dt. Minus, why this sign indicates? This sign indicates the decrease in the concentration. We have studied in the previous class. Plus negative sign indicates the decrease in the concentration. Positive charge. plus dB by dt, that indicates the increase in the concentration of the product. So what is rate? Minus dr by dt equal to k into r power 0. Here what is that? Zero order reaction. That means here concentration rate does not depend upon the concentration of the reactants. That's why k into r power 0. What is k? It is a rate constant, k equal to k, something power 0 equal to 1. That's why here k. Then rate equal to minus dr by dt equal to k, minus dr equal to dt into k, from left side to right side. So here dividing, here multiply. So dr equal to minus k into d. So multiplying with the k. So then we are, sorry, negative charge. So dr equal to minus k into d dt. Now we have to integrate the both sides above equation. This is equation, for example, 1. So we have to integrate the above equation with then what will be formed? Integration into derivation will be get cancelled. Here derivation is there already. So now we are integrating. So integration into derivation both will be get cancelled. So r will be remains like that, and k. Now we have to integrate with respect to t. Integration of dx equal to x, integration of dx equal to x, like this. Integration of dt equal to t. So k is a constant, negative charge is there, so minus k is a constant, and integration of dt equal to t minus kt plus c. So concentration of r, this square brackets indicates the concentration of r equal to minus kt plus c. So this is equation 1, where c is a integration constant. This c is a integration constant. Why? Because we are on integration, some value will be is there, that is value is, so integration constant. Now we have to take at time t equal to 0. So at time t equal to 0 means, so there was not started, still there was no reaction is happened. T equal to 0, t equal to 10 seconds, some reaction is happening. T equal to 0 means there was no reaction, it has ready to start the reaction. So t equal to 0, what will be happen? R equal to r naught. That means there was no change in the initial concentration. That's why r equal to r naught. So these two values are t value as well as r value, we have to substitute in the equation 1. Then what will be happen? R naught equal to minus k. So t equal to 0 plus c equal to c, here something power 0 0. So r naught equal to c. So this r naught value we have to substitute in the above equation. Then in this equation 1, then what will be happen? Concentration of r equal to minus kt plus r naught. So this is the integrated rate equation. From this equation we can calculate the rate constant k value. So k equal to r naught, here negative charge is there, that's why r naught minus r divided by t. So this is the rate equation for the zero order reaction. Rate equation is various, different from, for different reactions, zero order reaction, first order reaction, second order, so it is different. For the zero order reaction only, k equal to r naught, initial concentration of the reactant, minus R indicates the concentration of the reactant at any time divided by time. So this is a rate constant for the, what is that one? Zero order reaction. Next, slope. So slope between the concentration as well as time. So here y equal to, see this one. What is this? Y equal to minus mx plus c. This is a integrated rate equation. So here we have to compare y equal to concentration of r, y equal to minus mx plus c. Now we are plotting a graph between the concentration of the reactant with the time interval t. So then here minus mx means slope, negative slope, minus k is a slope, and c is a intercept. Like this we have drawn a graph by plotting a graph between the concentration as well as time. Like this negative slope will become, okay, this is intercept, this is slope, minus k is a slope. Yeah. So then what are the examples for the zero order reaction? We have discussed the zero order rate and as well as zero order rate constant k equal to, like that. So what are the examples for the zero order rate equation? So zero order reaction, ammonia, decomposition of ammonia as well as decomposition of HI. These two are the example for the zero order reaction. So what we have discussed, zero order reaction means there was no rate does not depend upon the concentration of the, what is that one? Reactants. Here why we are taking here catalyst, iron catalyst to rm catalyst we are taking. So in the decomposition of ammonia, what we are taking? Ammonia. So decomposition of ammonia, iron is a acting as a catalyst. So once ammonia can be, what is that one, covered completely on the iron catalyst. So after completely covering on the iron catalyst, the concentration of ammonia, whatever the chemical reaction, does not depend upon the concentration of the ammonia. Okay, just up to covering of the iron catalyst only, the it has to cover. Then does not depend upon the initial concentration. You take 10 molar, 0.01 molar, any molar does not depend upon. That's why. So these two are the examples for the zero order reaction. Next, first order reaction. So derivation of the integrated rate equation for the first order reaction. So first order reaction, A gives product. So rate equal to K into A. Okay, this is first order reaction, power 1. A power 1 means here need not to mention 1. So that's why rate equal to K, concentration of A. A is a here reactant. So what we can write, minus delta A by dt equal to Ka. So similar, by using the zero order reaction, we can also write rate equal to minus dA by dt equal to Ka. So integrating on the both sides. What is that one? So we have to take this concentration of A to the left side and dt to the right side. That's why minus dA by dt equal to K dt, negative charge, multiply with the negative charge. So dA by A, concentration of A equal to minus K dt. Then we have to integrate. So integration, concentrations, these two are the limits, initial concentration and after time t. So A naught, so A power here 0, A time t. So integrating with the two limits. Then what will be formed? Integration of 1 by x dx equal to ln x. That is a one of the mathematical formula. According to that one, we are writing ln concentration of A divided by concentration of A naught equal to integration of dx equal to x. So integration of 0 to t, limits, these two are the limits. Actually, we are taking here limits. That's why here we have to take. So here minus kt. So ln concentration of A divided by A naught equal to minus kt. So this one. Okay, here A naught is the initial concentration and AT is a concentration at time t. Then by using this one, we can substitute the log also. Log A naught by AT equal to 2.30. That will also come. So we have to compare this equation with the, what is that one? Y equal to mx plus c. Okay, yeah. Then what will be happen? Graph will become, by plotting a graph between the concentration and time t intervals. So here we can also write that here ln A equal to minus kt plus ln A naught. This is the first order rate equation. By plotting a graph between the ln t as well as time concentration ln A versus t. Here concentration is the ln A and time t, negative slope will become. So what is the slope? Minus k is the slope. What is intercept? Ln A naught. So similar to zero order reaction, here also what is that one? Negative slope will become, but here the rate will be depends upon the initial, whatever the concentration of the reactant. But in the zero order reaction, rate does not depend upon the concentration of the reactant. That is the major difference between the zero order reactions and first order reactions. What are the examples for the first order reaction? These three. See this one, thermal decomposition of nitrogen pentoxide N2O5. N2O5 on decomposition, what will be formed? Nitrogen trioxide N2O3 plus oxygen gas. So this is one of the example for the first order reaction. Similarly, hydrolysis of peroxide. Okay, hydrogen peroxide H2O2 will be decomposed into water plus half O2 oxygen gas. And third one, decomposition of calcium carbide. So CaCO3 on heating, what will be formed? Calcium oxide along with the carbon dioxide gas. So these three are the examples for the first order reaction. So these three, rate depends upon the initial concentration of the reactants. Okay, so that's why these comes under the first order reaction. Yeah, next one more important topic, that is what is that one? Half life of a reaction. Okay, how it will be changes in the zero order reaction and first order reaction. We have to discuss these two terms. So half life, what is half life? The time required to, so decrease the concentration of the reactant to half. Okay, reduce the half of the initial concentration. The time is called as half lifetime. Here is the definition is there. The time required, it is defined as a time during which concentration of the reactant is reduced to half of its initial concentration. For example, we are taking 100 molar concentration. It has to decrease to 50 molar concentration. To complete the reaction, for example, A gives B, 20 minutes is required. So to complete half reaction, 10 minutes is required. That 10 minutes time is called as half-life time, or that reaction is called as half-life reaction. So how it will be changes in the zero order, that means how, what is the effect in the zero order and first order we will discuss here. So in the case of zero order reaction, what is the rate equation for the zero order reaction? K equal to R naught minus R by T. So we are discussing half lifetime. That means if T, we are discussing T equal to 20 seconds, then half lifetime T half equal to 20 by 2, 10 seconds like that. So here T equal to T half. Then what will be changes? Reactant, concentration of the reactant will be changes to initial concentration here. For example, here 10 like that. So concentration equal to R naught. R naught is the initial concentration divided by 2. It will be changes to half. So a T equal to T of R equal to R naught by 2. So we have to substitute these two values in this equation. K equal to R naught minus R by T. So K equal to R naught minus R value we have R naught by 2 by T half. By simplifying this one, R naught minus 2 R naught minus R naught by 2, then get cancelled. Then T half equal to R naught by 2K. So this is the relation, interrelation between the rate constant of the first order reaction K and T half. Okay, numerical problems will become from this area important. T half equal to R naught by 2K. This is the final equation of the half life in the zero order reaction. T half equal to R naught by 2K. Here T half is a half life and R naught is the initial concentration of the reactant. What is K? K is rate constant. Zero order rate constant K. So what is numerical will be K will be give, initial concentration will be give. Then simply we have to substitute the T naught value. Otherwise T of will be give R naught. Initial concentration will be give. We have to calculate the K value, rate constant in the zero order reaction. We can calculate by using this equation. T half equal to R naught by 2K. This one. So sorry, here first order reaction, actually this is half life in the first order reaction. T half equal to ln K by 2. So ln 2 by K. How it will become? Similar to like this. So here first order reaction is there. Here see this one. So in this equation we have to substitute the values. Okay, in this equation we have to substitute the T value as well as concentration value. Okay, T equal to T of A equal to A naught by 2. Like that we can get the, what is that one, this equation, T half equal to ln 2 by K. So here there was no initial concentration term. See this one, here T R naught is there, A naught or R naught, that is the initial concentration term. In the zero order reaction R naught term is there, that's why it depends upon the initial concentration of the reactant. So but in this case of first order reactions, so that does not depend upon the initial concentration. Why? Because there was no R naught or A naught value. Okay, here there was no concentration term, that's why T half of first order, this is not second order, sorry. So T half of the first order reaction does not depend upon the initial concentration of the reactant. Why? Because in the equation there was no concentration term. T half equal to ln 2 by K. So ln x equal to 2.303 into log x. So here we have to substitute 2.303 log 2. Log 2 value 0.3010. By multiplying to these two, what will become 0.693 divided by K. So T half equal to 0.693 divided by K. So this is the relationship between the T half of first order reaction and K, rate constant. Okay, what is the value? T half equal to 0.693 by K. What is important point here? T half does not depend upon the initial concentration of the, what is that one, in first order reactions. So this one, these pictures indicates those. Okay, yeah. Then numerical problems regarding this one. This is question, actually problem. What is problem is given? A first order reaction is found to be rate constant is given. Then find out the half life of a reaction. Okay, this is a problem. What is giving? Rate constant is giving here. K value is given and he is asking to find out the T half. What is the value we know? According to mathematical equation, T half equal to 0.693 by K. This is a one equation regarding interrelation between the T half of first order reaction and rate constant. Simply we have to substitute the K value in this equation. T half equal to this constant value 0.693 divided by K. What is K? 5.5 into 10 power minus 14 second inverse. So equal to 1.26 into 10 power minus 13. Yeah. So next problem is show that first order reaction here. Second problem, this one, show that in a first order reaction time required to completion of the 99.9% is 10 times to its t half. Okay now? Yeah. So here we have to show that. For that solution, what is solution is there? When the reaction is completed 99.9%, how much of reactant is remaining? So reactant remaining equal to R naught minus 0.999% of or not. So to find out this one, we have used the first order rate equation. K equal to 1 by T ln A by A naught or R naught by R. So K equal to 2.303 by T log R naught by R. This is a first order rate equation. Then simply we have to substitute in the equation. So 2.303 by T and log R naught initial concentration minus R naught. So what is R value here? R equal to R naught minus 0.999 R naught. This value we have to substitute here. Okay, R naught here. You have to take R naught as a common. So 1 minus 0.999. That means 0.001 will become. Okay, R naught get cancelled. Then 0.001 means 10 power minus 3. It will be come to the numerator. So 10 cube will become. So R naught will be get cancelled. 10 cube will become. So 3. So log 10 power x equal to x log. That means log 10 equal to 1. So 3 log 10. So 3 into 1. So 2.303 into 3 means 6.909 by K. See this one. For a half of a reaction, we have to substitute this one. T half equal to 0.693 by K. This is a equation for the first order reaction. So now we have to substitute. T by T half equal to 0.69. This value, whatever the we got this value, simply we have to substitute in this equation. Then we can get the value 10. So that's why whatever the. So what is the question he is asking? Show that first order reaction, first order time required to completion of 99%, 99.9% is 10 times the T half. So that's we have calculated the T half is 10 times. So this is the summary of the, what is that one, rate order, what is the rate, what is the integrated rate equation for the zero order, first order, second order reactions. Okay, second order is nothing but, so some of the concentration terms is 2. So that is second order reaction, this one. So we discussed all this. Okay, what is the slope, what is the rate equation, what is rate law? This is rate law. Rate equal to K, rate equal to K power A, here A power 0, A power 1, A power 2. Integrated rate A equal to minus KT A naught here, this one. This is, so by plotting a graph between these two, here concentration of A versus T, here ln A versus T. So what are the slope? We have seen this, all this. What is the T half value of the zero order reaction and first order reaction? T half equal to A naught by 2K. Here T half equal to 0.693 by K. So same this one. So T half equal to ln2, similar that one. So graph between the AT minus KT A naught, ln A, this one. Next, pseudo order reactions. What are pseudo order reactions? Yeah, see this one. So in some chemical reaction, for example, A plus B gives C. So if the rate of the reaction depends upon the both A and B, then that is called a second order reaction. But in this case, what is happening? Hydrolysis of ester, ethyl ester. This is one of the ester, ethyl ester. This is, so what is happening? Ester on hydrolysis, what will be formed? Carboxylic acid and alcohol will be formed. So in this reaction, so what is the concentration of the ester? 0.01. What is the concentration of the water? 10 molar we are taking here, 0.01 molar taking. This is at time t equal to 0. At time t equal to, for example, after time t, after 10 minutes or 20 minutes like that, what will be happen? Some chemical reaction will be happen. So how much of the A is there, then that much of the B also reacted. So here 0.01 mole is there. That's why it will be also 0.01 will be reacted with the A. So here after completion of the reaction, how many moles? 0. Why? Because this is reacted with this one. So how many? 10 minus 0.01 means 9.9 moles is remains here. How many moles of this one? 0.01 moles of acetic acid is formed, acid is formed, and alcohol how much? 0.01 is forming. So in this reaction, the concentration altering of the concentration of water does not takes more, very very little bit, 9.9, 10 means there was no lot of change. That's why here on the concentration of the rate does not depend of the concentration of the water, only it depends upon the concentration of the ester. Okay, it is look like second order reaction, but it is not second order reaction, it is first order reaction. Pseudo means false. Okay, it is not false. Okay, it is not second order reaction, it is first order reaction. In this, so the rate depends upon only ester concentration. That's why it is called as, what is that one? Pseudo first order reaction. It is a first order reaction. Why? Because rate equal to K into ester power 1 here, like this. Rate equal to K into ester power 1. Water power 0. Something power 0 equal to 1. So, okay. So, that's why it is depends upon the only concentration of the ester. That's why this is called as pseudo order reaction. So, pseudo first order reaction. Another example for the pseudo first order reaction is hydrolysis of this cane sugar. Okay, cane sugar on hydrolysis forms glucose and fructose. Here also the rate does not depend upon the concentration of the water. It is depends upon the only concentration of the cane sugar. C12H22O11. This is the cane sugar formula. It is converted into glucose and fructose molecules. Yeah. Next we will discuss about the temperature depends upon the rate. First we have discussed about the concentration dependence and temperature dependence. So is there any effect of the temperature on the rate of reaction is there or not? We will see in this reaction. We'll see in this slide. See this one. So for example, decomposition of nitrogen pentoxide N2O5. We see chemical reaction. This one. See, this is the N2O5 chemical reaction. So N2O5 on decomposition N2O3 plus O2 gives form. It was form. So see this one. So it 0 degree centigrade, it requires 10 days time. Similarly, at 25 degree centigrade, 5 hours time. At 50 degree centigrade, 12 minutes only to completion of the N2O5 to N2O3 plus O2. That means by increasing the temperature, what is happening? Rate of reaction is increases. Okay, the time is reducing means rate of reaction is increases. So that means it is clear that it depends upon the temperature. Rate depends upon the temperature. This is one of the example. And another example is, so combination of the KMnO4 plus oxalic acid between these two reactions. So KMnO4 will be decolorized. Actually, it is pink in color. When it will be reacted with the oxalic acid H2C2O4, the color will be decomposed. Okay, decolorized. At lower temperature, it takes more time. When while increasing the temperature, what will be happen? It fastly decolorizes. Okay, it will be converted into white color. Okay, pink color to like. So based on these two examples, it depends upon the temperature. So temperature effect on a rate of reaction can be explained by the Arrhenius equation. Now we will see the Arrhenius equation. What is Arrhenius equation? Temperature effect on the chemical reaction. That means rate of a reaction can be explained by the, what is that one? Arrhenius equation. So what is Arrhenius equation? K equal to A into e power minus EA by RT. This is a Arrhenius equation. Okay. Yeah. Here what is K? K is a rate constant. A is Arrhenius factor. Okay, Arrhenius factor A and K is rate constant. Here EA is a activation energy. What is activation energy? While here see in this graph, reactant is converting into the product, so it has to goes to the some intermediate stage. So here to goes some energy is required. That energy is called as, what is that one? Activation energy. This is important. So while increasing the temperature, so the reaction takes place through the lower activation energy. That's why rate of reaction will be increases. So K equal to A into e power minus EA by RT. This is a mathematical equation, Arrhenius equation. Okay, yeah, EA is a activation energy. See this one, this is a graph between the plotted between the ln k versus time t 1 by t. So negative slope. Why? Because ln k equal to ln A minus EA by RT. Ln k, rate constant k and temperature t. So between these two, negative slope will be coming. So what is slope? Minus Ea by R. What is intercept here? Ln A is the intercept. So this is one of the problem regarding the Arrhenius equation. What he has given, the rate constant is given both for the, so the rate constant are at 500 Kelvin and 700 Kelvin mentioned, 0.02 at 500 Kelvin and 0.07 at 700 Kelvin. What he is asking, calculate the activation energy Ea and Arrhenius factor A. So one formula is there, log K2 by K1 equal to Ea by 2.303 or T2 minus T1 by T1 T2. How it will be obtained? By using this equation only. Okay, we have to take two limits. Here K only is there. If two rate constant are there, then we have to integrate by between the two limits K1 K2. Here between the two limits T1 T2. Then this mathematical equation will be obtained. So log K2 by K1 equal to Ea by 2.303 R into T2 minus T1 by T1 T2. Simply we have to substitute the K1 and K2 values, T1 and T2 values in this equation. What is K2? 0.07 and K1 0.02. Ea, we have to calculate the Ea value. Then we have to substitute the 2.303 into R. R we have to take here joules. That's why 8.314 joule per Kelvin per mole. Simply substitute the T1 and T2 also. T2 equal to 700 and T1 equal to 500. By simplifying all this, what will we get? Here 0.54 equal to Ea into 5.7 into 10 power minus 4 divided by 19.5. 19.5 because of it. 2.3 into 8.3. By simplifying all this, what will we get? Ea equal to 18,230 joules. This much of energy is required. Okay, when temperature T1 T2 Ea K1 K2 is given. Next we have to find out the, what is that one? A, Arrhenius factor. So by using this one, what is the equation? K equal to A into e power minus Ea by RT. This is a one of the starting equation, Arrhenius equation. Simply we have to substitute the K as well as Ea. Ea already we have calculated here 18,230 and K any one of the rate constant you have to take. Concerned, if you take 0.02 rate constant, then you have to take temperature here. T is mentioned 500 Kelvin. If you take 0.07, then you have to take 700 Kelvin. Simply by substituting these two values, what will be get? So the resultant A, Arrhenius factor will become 0.02 divided by 0.012. What is the final value? 1.61. This is a Arrhenius factor. I hope it is clear. So numerical is important in the case of Arrhenius factor. So see, this is also similar to the that problem. So first order rate constant is given. Okay, what he is asking? K1 is given and T1 T2 is given. He is asking find out the K2 value. First order rate decomposition reaction. K1 is given 1.60 and two temperatures are given. 700 Kelvin is given as well as what is given 600 Kelvin is given. He is asking to find out the what is the changes of the rate constant. Okay, what is K2 is asking. So this equation log K2 by K1 is there. So log K2 by K1 is log K2 minus log K1 equal to similar this equation we are using. So log K2 by K1, this is equation log K2 minus K log K1 equal to Ea by 2.303 R. So 1 by T1 minus 1 by T2. Substituting all this T1 value, T2 value and K1 value. Ea also given. Activation energy is given. So that one. Based on all this, we can calculate the K2 value. Okay, last one, effect of the catalyst. So like temperature also, if catalyst also affect the rate of a reaction by using the catalyst. So the activation energy of the reactions decreases the activation of the reaction paths. That's why rate of reaction will be increased. What is the catalyst? The substance does not involve in the chemical reaction, but it can increase the rate of reaction. That is called as catalyst. By using the catalyst, we can increase the rate of reaction. That is the conclusion from the catalyst effect on the rate of reaction. So like this. This is with the catalyst. This is without catalyst. Without catalyst, more activation energy is required. Here, less activation energy is required. Yeah. So this is one of the example. So decomposition of potassium perchloride. So KClO3 gives KCl plus 3O2. Here manganese dioxide used as a catalyst. By using the manganese dioxide, we can increase the rate of reaction. Without this one also, this reaction proceeds. Whatever the KClO3 gives, KCl plus 3O2, oxygen gas. But by using the MnO2, we can increase the rate of reaction. If, for example, it takes 10 minutes, by using the manganese dioxide, we can reaction proceeds through 7 minutes only. That means we can alters the, we can increase the rate of reaction. So this is about the chemical kinetics. So today's class we have discussed about the concentration effect, as well as temperature effect, as well as catalyst effect. Okay. So in this finally chemical kinetics, we have discussed that one. What is that one? What is the rate of the reaction? Okay. What is the reaction mechanism? What is the order of the reaction? Okay, see this one. Rate of your reaction, order of your reaction, and molecularity of the reaction, and what is the effect of the temperature on the rate of your reaction, what is the effect of the catalyst on the rate of your reaction, what are the integrated rate equations for the zero order reaction and first order reaction. And also we have discussed that t half, okay, t half of the zero order reaction and a first order reaction, what is the relationship between the t half for the zero order reaction and first order reaction, what are those. So numericals also important regarding the first order reaction and as well as zero order reaction, and interrelation between the t half as well as first order of the rate constant. So this is regarding the chemical kinetics chapter. So from this chemical kinetics chapter is completed. So thank you one and all.